2014, he was invited as visiting researcher at the Department of Electrical Engineering, Qatar University, Doha, funded by the Qatar National Research Foundation, that is Government of Qatar. He continued his research activities with the Dublin Institute of Technology, Ireland in 2014. Further, he served as an associate professor with the Department of Electrical and Electronics Engineering, University of Johannesburg, South Africa from 2016 to 2018. Since 2018, he has been a faculty member with the Department of Energy Technology, Aalborg University, Esbjerg, Denmark. He has authored over 300 scientific papers. He was the recipient of the Best Paper, the Most Excellent Research Paper Award from IET SEI SEON 13, from IET CAT 16, IEEE EECSI 19, IEEE CMCON 19, and 5 Best Paper Awards from ETA EERE 16. Sponsored lecture notes in electrical engineering, Springer Book. He is a fellow of the Institution of Engineers India, the Institution of Electronics and Telecommunication Engineers India, and the Institution of Engineering and Technology UK. He is an editor, associate editor, editorial board for referred journals, in particular the IEEE System Journal, IEEE Transactions on Industry Applications, IEEE Access, IET Power Electronics, IET Electronics Letters, and Willy International Transactions on Electrical Energy Systems. He is a subject editorial board member, Energy Sources, Energies General, MDPI, and the subjects editor for the IET Renewable Power Generation, IET Generation, Transmission and Distribution, and Facts General. So I request P. Sanjeevi Kumar sir to kindly start the session.
Um, Thank you very much. First of all, could you verify my screen is visible?
Yes, sir.
Thank you very much. Thanks a lot to Dr. Bharatwaj for the invitation, and of course, I thank MIET institution for the management for invite me for this wonderful event. Good morning to one and all. So I'm from Aalborg University in SBI, and I take few seconds about to introduction about the university. So this is Aalborg University in SBI, which is where we are working on energy department, which is available here on the screen. And about Aalborg University, this is Aalborg University's central institution, which controls all the academic and research activities of the university. And about our strength, we have different programs, which includes humanities, social science, medicine, engineering science, IT and design. Of course, we have students of 20,200 students, which includes part-time students, 2,850 part-time students, 850 PhD students, 2,230 staff members, and about 690 international researchers, 1,270 administrative staffs, and about the budget is 450 million USD, which is the statistics which are obtained from 2019 from Aalborg University. And this is Denmark, a tiny country, a small country, where Aalborg University is located in Aalborg. I'm working on the southern part of the Denmark, which is Esbjerg, and this is the capital city, Aalborg. So we have 3 different campuses of the university, and the central operation unit is from Aalborg. And the strength of the Aalborg University, students and staff members, I'm sorry, are given here. And about Aalborg University always ranked among the top 5 with its teaching methodologies by the MIT. So we have a specific program called learning goals based on project-based and problem-based learning system, which is called PBL. Every semester, the student has to take up particular courses based on their program, and they have to do a project, either with the internal projects from the department or from the research institution. So for a bachelor students or for a master students, every semester they have to execute a real-time project which is required for the societal benefits. Most of the projects are from industries. Obviously, 50% of the projects are in collaboration with the Danfoss, Grodenfoss, Vistas, Snyder's, etc. The top companies which are external collaborator with Aalborg universities with the teaching, of course, with the research aspects. And about recent milestones, 35 cases are registered by Aalborg University students along with the faculty members for creating a real-time solution for the societal benefits of Denmark and EU countries, of course, for the international perspectives. And about the research, Aalborg University is one of the most fast disseminating research-based university. You are always been the top 5 university, and to 2019, Aalborg University has been listed as a number 1 in, which is not updated here, in engineering division. And in particular, world ranking is between 200 to 250. Recently, it is around 207. And among the young universities means the university which are inception less than 15 years of old. Aalborg University is among the top 20 always in the world. And about Aalborg University in SBR, we have different programs which has particular weightages for the societal benefit, which includes the sustainable energy engineering for the bachelor students, and we have a offshore energy technology and process engineering and combustion technology, which are very significant program of signature from Aalborg University in SBR. Oil and gas and risk and safety management are the other important programs which are available only in very few university, as a notable only in Aalborg University. These are benefits the national developments. And of course, we have electronics program for bachelor, and the master program belongs to advanced electronics. And bachelor programs also available in biotechnology, which includes master degree in chemical engineering and bioenergy. Other bachelor programs which includes construction and diplomas. With this small introduction, let me move on to my technical presentation. So today my technical presentation is focused on electronics for electric vehicles and new generation of low cost solution. So in this case, the critical play will be played by the electronics converters, and obviously without electronics we can't able to have a new generation renewable energy systems. So today my presentation will be focused on how we can adapt alternative solution for IC engines. So we need to find a suitable solution. Of course, this can be fulfilled by mostly by fuel cell, because most of the country has adapted fuel cell based electric vehicle. But fuel cell based electric vehicles needs a partner, which is going to be a DC-DC converters. And I'm going to show you some converters what we have developed from our research units, and of course how we have developed the configuration, experimental developments, and definitely for the challenges which we are facing in electronics. So if you look at a fuel cell is a large scale renewable energy. It can comes under renewable energy because even though it's not absolutely as like a wind or PV, still we consider fuel cell as a renewable energy because doesn't emit any hazardous gases. That's most important. So CO2 emission is not available in a hydrogen power generation or transportation system when it is used as a fuel. And if you look at the classification, there's a very large classification of fuel cell, and each classification or type of fuel cell can be adapted for different application because they have their own specific category. As a electronics engineer, I am looking not on the generation side of the hydrogen or on the DC voltage generation from the fuel cell. That is the challenges for the chemical engineers, of course, for the development of fuel cell based technologies. As an application based engineer, I look always for the categories. So in this case, the fuel cell based electric vehicle can be used for a small vehicle, of course, for a bike, car. Large vehicles includes trucks, buses. And if you look at the temperature, that's most important. It can be adapted to all situations because from minus 20 degree to greater than 800 degree. So a wide margin, fuel cells can be adapted even for a cold country, hot country, or extremely hot country, or extremely cold country, or intermediate. So it has a major role in selection between the power rating and of course with the temperature. With the power rating, it can be adapted between lowest of 50 watt to less than 100 megawatt, which shows you a wide range of application and the power rating can be adapted between Hello? Hello? Hello?
Yes, sir. You are
Could you able
audible,
to?
sir.
Ah, that's fine because I got again the the linkage is
Yes, sir.
so perfect. So
Sir,
the metal hybrid.
screen is not visible, sir.
Uh, so did you able to follow my presentation? Whatever I done for a few minutes, or
Okay, sir.
I'm not. Could you please tell me? Did you hear my presentation?
No, sir. Presentation not available, sir.
Voice.
Voice is audible.
Something went wrong. I'm sorry because I already shared my screen. Okay. Could you able to see my screen now?
Now it is showing started screen sharing.
This is because of the bandwidth difference
Now
between.
it is visible, sir. Now it is visible.
Okay. Just hold on a second, please. Just hold on a second. Hello. Hello. கொஞ்சம் நான் அப்புறம் கால் பண்றேங்களா பிரசன்டேஷன்ல இருக்கிறேன் நான் அட்டெண்ட் பண்ணலன்னா பிரசன்டேஷன்ல இருக்கிறேன்னு அர்த்தம் ஓகேங்களா நான் கால் பண்றேன் now the screen is visible to you all.
It is visible, sir.
Oh, okay, thank you because you need me to start again from the beginning or hello.
You start from where you left, sir.
Oh, that's fine. Okay, great. So please inform me because on another side I don't know what is going on. Please inform me. So this is a large classification of fuel cell. Are you able to see my screen now very clearly? The fuel cell technologies. This is the first slide of the technical part. Could you able to see my screen now?
Yes, sir.
Okay. This is a large classification of fuel cell in real-time applications because we choose fuel cell as an alternative solution for IC-based engines because petrol or crude oil-based diesel or emit more CO2 and causes big pollution in our environment. So all the governments are focusing towards to reduce CO2 by 70% by 2030, of course 100% by 2050, but the targets can be achieved only by using renewable energy systems. In this case, fuel cells plays a critical role because it is a vast classification and each type of fuel cell adapts for particular needs and applications. For example, fuel cell can be adapted between minus 20 degrees centigrade to greater than 800 degrees centigrade. So it's a wide margin of temperature control. Of course, the power is very important. We can go up to minimum 50 watt to maximum less than 100 megawatt. This is a large scale power deviation. And we can also go for either application of a small vehicle or a large vehicle. So we can adapt the fuel cell for various needs. For example, if you are going to use a magnesium air fuel cell, it can be adapted for a temperature between minus 20 degree to 0 degree, whereas the power can be less than 50 watts is an example. For example, if I'm going to use metal hybrid fuel cell, again, the power is going to be 20 watts less than, and the temperature is going to be minus 20 to 0 degree centigrade. Another example I can give you a zinc hair battery, which is a recent technology on fuel cells, and the temperature is going to be between 0 to 80 degree, and the power requirement is less than 50 watts. If I want to go for a very high power, for example, 10 to 1 kilowatt, 10 to 1 kilowatts, we can use solid acid fuel cell. And the temperature range is between 80 to 300 degrees centigrade. So we have a large scale deviations of application of fuel cells according to the environmental requirements. That's why we choose fuel cells as an alternative solution for IC engine powered by, IC engine which is not powered by petrol or diesel. We are trying focus towards more electric vehicle with electrical components. And this is an example how an electric vehicle looks. We have two types of electric vehicles. One is for the domestic application, which is home application. Another one is for the commercialization because of the transportation. So usually an electric vehicle with fuel cell based technology will have fuel storage tank along with the reformer and the fuel cell. So these are the three conversion unit in the electric vehicle to generate DC voltage. Once the DC voltage is generated from the system, it has to be transmitted to the motor through a DC-DC converter, which converts the DC to a very high value. Of course, from this DC value, we have to convert it into AC because of the motors which is adapted in the electric vehicle. So the motors are either it will be an induction motor or synchronous motor. Now, recently, brushless DC motors also adapted for electric vehicle for high performances, more luxurious life, and more stabilized systems. So in this case, all we need electronics converter. Apart from the luxurious need is available, air conditioning, lights, sophisticated control units. Then we also having ABS and airbag system for the protection. All these are governed by electronics converter with a small term called as actuators, DC actuators. So they are not nothing but a DC-DC converter. If you look at the efficiency generated by these electronics converter is around 80% when compared to the fuel cell reformer or fuel cell storage tank, because the efficiency from the fuel reformer is around 80% and fuel cell is around 60%, but the overall gain developed by the electronics converter is around 80%. So this is a model of fully driven fuel cell application oriented vehicle. And we can have a hybrid model which includes one side is going to be the fuel cell as a energy source. Parallelly, we are going to have a battery units or ultra capacitors. So battery plays a critical role. So modern technology focused on lithium ion batteries. And of course, we can go for ultra capacitors because the ultra capacitors can help to reduce the size of the battery. In real-time application, not only the companies use batteries because batteries are expensive and the technology requires more charging station. Of course, fast charging is not still developed as expected in seconds. At least 30 minutes is required per 250 kilometers. So that is a trend going on. So we need an extra boosting energy sources that can be done by ultra capacitors because ultra capacitors can charge a large scale of energy than the batteries. Of course, they can be a parallel operation with the battery. That is a different topics. In this case, so we have a balance between the fuel cell and batteries. That's why it's called a hybrid electric vehicle based FC, fuel cell based hybrid electric vehicle. And in this case also, the DC-DC converter play a critical role to power the battery. Of course, the stored energy can be delivered to the motor through the inverter. And in this case also, the efficiency critically played around 80% when compared to the fuel cells. And for the transportation is very important. Case of transportation, the same system as like the previous one. We can have a fuel cell. Along with the fuel cell, we can have a DC converter and inverter to control the motor. Of course, we can use another DC-DC converter for the luxurious load and control unit to control the fuel cell and the motors, then battery unit for the backup storage, and of course they can be used during the driving condition on needs. But for a large scale transportation, this is going to be a DC microgrid within an electric vehicle because the power capacity is very high. And in this case, for the commercial transportation systems, the parallel operation of battery and fuel cell is required because we can't be able to drive a transportation system only with a battery is impossible. So in this case, we need fuel cell as a storage energy to generate DC-DC converter. And this is the common point of coupling, which is a DC microgrid. On the power side, we can have a battery around 600 to 700 volts, and of course, which includes the battery controller for the management systems. From the DC point of coupling, we can able to connect to a motor through the inverter. Of course, another inverter is required to support a 20 kilowatt AC loads in the electric vehicle. And apart from that, we have luxurious loads as I explained in the beginning, which is around 24 kilowatt, which will be powered from DC-DC converter from the fuel cell. So you can have a complete idea how these electronics converters play a critical role in developing these electric vehicles, which is operated either with a fuel cell based vehicle or a hybrid model where the battery and ultra capacitors and fuel cells plays a critical role. And about our own developments, what we are doing in the research units, we are developing many electronics converters for the past 6 to 7 years. And in this case, we always focused on a cheaper solution because cost effective. In order to compensate all the effects, of course, under the faulty condition, we are trying to figure out what are the possibilities. It can be easily isolated, and of course, if there is any component failure, it should be readily replaced. So in this case, the classical models which are available in the literatures, or of course in the standard basics of electronics converters on DC-DC, we have two modules. One is isolated converters and non-isolated converters. So what is an isolation converter? Isolation converter is input port and the output port are terminated by or isolated by transformer. Then we call it as an isolation converter. Whereas in case of non-isolated converters, the input port and the output port are not isolated; they are coupled together. And there are possibility we can have a coupling by common, either on the port input port with a common and output port with a common ground. Other possibilities, we can go for input as a ground and output as a floating. And of course, for other configuration, we can have here both the output and input port are grounding, but still we can have a multiple stages. I will explain you during my presentation. We can have a multiple stages. Also here we can have a multiple stages, whereas input is grounded and output is floating. Same applicable for in case of no isolation converters also. They are technically called as resonant converters, because they use transformer to transfer the power from the input port to the output port with high transformation ratio. And because of the transformer, you can have a multiple control to transfer the power by controlling the turns ratio of the transformer. About the basics, so these are the standard converters which are used in industrial application from the basics of circuits. So when the device is in parallel with the supply, this is a boost converter where the input voltage is less when compared to the output. And here we can use the high voltage for driving the electric vehicles. This configuration can be slightly modified by replacing the diode from the positive side to the negative side with a reverse bias condition. So reverse blocking here has been reverse flow of current is controlled by the diode. So in this case, we can have a inverting and non-inverting mode. And this configuration where the device is connected in series with the supply, so the output voltage will be much less than the input. So this configuration is called as a buck converter. In this case, the inductor on the positive side can also be transferred to the negative side, as shown. So we can have a inverting and non-inverting modes with the floating points. This case, the last one, the adjustment of the inductor and capacitor. So they are dislocated on different locations. They replaces the diode by an inductor and inductor by a diode. Of course, this diode can be transferred to the negative side. Then we have another configuration. So these are the basics. And of course, these converters are readily available in the market for the application of electric vehicle. What are the drawbacks? Due to the passive effects, the gain margin has been reduced and the efficiency comes down, and we don't have a wider margin to control these MOSFET or IGBTs. So these MOSFETs, for example, if you are using 90%, is very dangerous because of the high flow of current. The components can lose their reliability and they can blow off. Of course, using 90% duty ratio is very dangerous for the power supply. Due to the transient, we can damage, of course, if it is a PV or a battery. Then we have to find an optimal solution how to enhance this configuration so that the MOSFET can use 60% utilization, but still the power delivered to the load will be much higher. So for this solution, we can go for two types. One is cascading approaches on a parallel based or series based orientation. So if you look at this configuration, this is the power supply from the battery or PV or fuel cell, which can be cascaded with multiple DC-DC converter in parallel operation, and we can able to enhance the voltage to the output side. Other possibility, this is in series fashion, so we can able to enhance multiple DC-DC converter in series connection along with the positive sign. And finally, we are controlling with one MOSFET so that we can able to deliver the maximum power to the load side with a very high voltage. How we can able to do that? With simple passive components without using a transformers. The possibilities are using switched capacitors. What is a switched capacitor? I can give you a basic model. So two capacitors are connected with two diodes, and we are controlling the current flow based on the diode configuration, and the stored energy in the capacitor will be delivered to the load side. Then we will get a much higher voltage. For example, the voltage across C1 plus voltage across C2 will be added up, and it will be delivered to the load side. It's a simple example. We can go for a complex example. We can have a many configuration I shown here. The complex example, we can go with multiple usage of MOSFET or IGBT, which is connected across the capacitor. So based on the switching or turn on condition of the devices, we can able to store large energy in this capacitor and we can deliver to the. So this is a switched capacitor based passive component circuit. What is a switched capacitor? Because based on the switching on time, we are storing the energy on the capacitor, then we deliver to the load side. Other possibility on the passive component is going to be the switched inductor configuration. In this case, again, the inductors are connected in this fashion with uncontrolled diodes to control the flow of current. During the turn-on condition of the semiconductor devices, the instantaneous energy available in L1 and L2 are added up and delivered to the load capacitor, so it can able to have a very high voltage. And the different formats of having these passive circuits of the inductor in switched mode component circuits are shown here, and the most complex I can show you here. For example, when the device is closed, the instantaneous energy available in the inductor will be delivered to the capacitor C2 when the device is open, and of course here C3, of course in C4, subsequently from inductor L2 and L3, and the stored energy in the capacitor, which are going to be a parallel combination. So when they are in parallel, they are going to add up the power, and it's going to be delivered to the load side. So you can able to get a very high voltage on the load side. Other possibilities, we can go for a multi-stage, which I showed you in the previous few slides before. What are the classifications? What we can go for a isolated and non-isolated version. I talked about multi-stage. Multi-stage means we are going to use capacitors in a staircase fashion, so that it become a multi-stage configuration, and we can adapt these converters into real time for getting very high voltage. First case, if you look at very closely, the power supply from the battery or PV or from the fuel cell is connected to a standard boost converter. So this is a standard boost converter. In the middle, we are adapting switched capacitor, which I showed you in the previous slide, in stacks in series combination. And at the end, we delivered the power. Other possibility, we can cascade two boost converter in the input side. Then we are cascading multiple switched capacitor. Then the power can be delivered to the load side. These are the possibility. The last case, I can give you a typical example. You can have a different configuration model. Last case, the input power source is going to be a standard boost converter, and the capacitors are arranged in the form of a ladder, and the current is controlled through the diodes, and a very high power is delivered to the load, because whatever the energy generated from this circuit, the power will be delivered to the capacitors in a geometrical addition fashion, so that the total voltage will be added up and delivered to the load side. So, and these models are typically called as a CW models, which is developed by Cockcroft-Walton. So this is an example of how to adapt switched capacitors along with the existing standard configuration of DC-DC converters. So we have developed many converters in real-time applications, in particular to switched capacitor based, switched inductor based, multi-level converters and XY family. And we are trying to compare with the standard configuration. Competitor is going to be the resonant converter, which is based on transformers and coupled inductor. Obviously, in our investigations, what we have done for a couple of years, obviously the converter which is from XY family has a very high reliability, average cost and efficiency is very high. Of course, we always use a single devices, so the configuration can be easily extendable. And the drawback is on a large number of diodes, so that you'll have a much more losses and discontinuous current effect will appear on the input side. And it can be applicable for commercial transportation for low or high power powertrain requirement. It means that you can use for our transportation purpose or for domestic application for home needs. And when we are comparing with other converters, I have shown here. So the first converter is applicable only for a low power application. Second one is also applicable for low power application, but the standard configuration is applicable for very high power application, because they use transformers to transfer a very high power to the load side. In this case, the reliability will be very low or average, and the cost of the system is very expensive because it requires sophisticated control systems and sophisticated high frequency transformer designs, and efficiency obviously very high. That's most important. And the advantage is we can have to adapt a high power application along with soft switching techniques. Most important, by adjusting the turn ratio of the tank circuit, which is done by inductor and capacitor combination, or by a high frequency transformer. By adjusting the tuning ratio, we can able to adjust the power flow from the input to the output. But the circuit is going to be big in size, bulky, more power loss due to the magnetic components. That means the transformer use. And as I said, it is available for high power application. And we also worked on multi-level converters in comparison to the existing standard solution. So multi-level converter, it can be also applicable for high duty, but the drawback is reliability is average, cost is very high, and efficiency is very, very high. But the most important factor is the cost and reliability. And of course, the advantage, it can extend to any version of high power with a very low semiconductor devices used. And the drawback is we are going to use more capacitors and diodes. So capacitor reliability plays a critical role in this converter modules. And most important is what we have been doing in real time, because real time plays a critical role, how we use these electronics converter efficiently for the power supplies. So most of the countries or developing or advanced countries, still every country focus towards developing an isolated or island moded microgrids. For a non-technical person, I can say we need a power supply within our own generation unit to power our home. This is the technology we are focusing, and this comes under DC microgrids as a cluster, or it can be individual units, or even can be a small clusters. So in this case, we can have different renewable power supplies, fuel cells, PV, battery, and all are coupled to a common point of coupling between a voltage 24 volt to 48 volt, and a large power scale of common point of coupling will be 400 volt, which is a DC bus bar. And from the DC bus bar, we can able to connect to charging the electric vehicles, DC microgrids, DC home applications, and AC microgrids, which is the existing AC transmission line systems. So in this case, we need an electronics interface, because these are low potential and these are very high potential. So we need a DC-DC converter to step up this voltage to a very high value. Why we focus on these applications? Because, for example, countries like from India, from our country, we have a very structured main grid from Kashmir to Kanyakumari. The main grid is, there is no issue. It's well designed and well sophisticated with modern technologies. But the powering the remote areas, villages, which is not, many villages are not being access to the main grid, and because of the distribution and economical aspects, and of course the environmental condition of transportation. For example, places like Assam and Orissa, very complex because of heavy rain and wind. So in this case, the local energy plays a critical role. Local available energies like PV, we can adapt battery technologies, fuel cells, and wind plays a critical role. All these powers can be connected to a local cluster, and we can power all the units whichever required for the power supply for the utility. And in this case, we develop a new power electronics converter, which is based on a three-state hybrid DC-DC converter. Why we called a hybrid, I will tell you later. But why it is a three-state? Because we have three devices and three MOSFETs or IGBT triggered or turned on different instant, and we are able to get a very high voltage at the output. That's why we call it as a three-state converter. How we develop this converter? That's very important. If you look at the load side, is a standard boost converter, and on the input side is a standard full bridge inverter. On the full bridge inverter, we try to remove one device and replace it by an inductor, of course in the second leg also. Then this become a novel converter. What is the real aspect behind it? When the device is turned on, the instantaneous energy available in this inductor, of course, when this device is turned on, the instantaneous energy available in this inductor will be delivered to the load side boost converter, so that you are going to get a very large voltage at the capacitor C0. So this is the way we design the converter. For controlling the flow of current, we use these three diodes. So the current will flow from the source to the load side and doesn't reverse back to the supply. It's well protected. And this is a diode used for reverse blocking of the current towards the supply, so that it's well protected by virtue of its construction. And once the converter is designed, we are looking at various factors. Most important factor is the gain, how much gain I can able to get from this converter. For that, we develop many theoretical equations. I can't present in a short span, but I can give you an outline about the outcomes. We are trying to figure out the utilization of this DC bus, the renewable connected on the input side, from 10% of its power to 60%. So when 60%, the gain goes to 42 times. What does it mean? When the input is going to be 24 volt, the output is going to be 24 into 42 times. Or another example, if the input is going to be a 10 volt, the output will be 420. So 42 times at power transformation. Once the converter is designed, we develop the theoretical backgrounds. Then we check the gain margin and compared with the existing solution. Comparing with the existing solution, The proposed new model is very, very high gain. You can see from here when just using 60% of the DC bus. So we have a wide range of margin to control the conduction of these devices so that the efficient power will be delivered to the load side. The next target is to look at the experimental variation because it's very important for any converters which is developed in the laboratory model. As expected, the output voltage is around 400, and most important is the input current on the inductor side, which always shows the three states. One is the zero states, another goes to the peak value of 185, and the minimum value of 116.8 amperes. So it's a three-state level is confirmed with the inductor current, and these current are very smooth. That's most important. They didn't produce any short spikes or abnormal behaviors. And this is the voltage across the MOSFET, and the peak goes to 185 volt as expected. The input is only between 24 volt to 48 volt, and this is the voltage across the diode, which is showing the forward bias operation with the maximum peak value of 185 volts. So all the behavior as expected we are getting in with respect to the theoretical background agreements. And further we develop other converters like quasi circuit converter. What is the purpose of this converter? If you look at very close, on the load side is a standard boost converter again. Of course, on the input side, between the input side and the load side, we included a switched inductor based configuration so that we can able to generate high voltage to the output side. When the device is closed, the instantaneous energy generated from these two inductors will be stored as a potential difference in the capacitor, and the stored energy in the capacitor will be delivered to the load capacitor. Similarly applicable on the input side, the whatever the energy stored here will be delivered to this capacitor, then transferred to the load side. So we can able to get a very high voltage comparing to the existing converter which is already available in the literatures. So we designed the converter. The most important parameter will play on the losses. So for this converter, about 17% to 16% losses is generated by the all the devices which is used in the applications, than with the diodes, which is around 4.8 to 5%, and of course D0 is giving 5.2%, and the capacitor is between 6% to 6% between C0, Cy, and Cx. And about the inductor resistance, the inductor Ly gives around 9%. So this is the complete last distribution of the converter which we proposed. And because we have two inductors, we are looking very closely what is the losses here, which is around 9%. And we are also looking very carefully about the capacitor. As I said, in real time, capacitors cannot have the same behaviors because they are two passive components, and two capacitors cannot have the same behaviors in the real time. That's plays a critical role for the electronics engineers to maintain all the performance throughout the same to get a good reliability and durability of the capacitors. In this case, the capacitor C1 generate a voltage between 66 volt to 65 volt, and 1 volt is the ripple voltage. And in this case, it's 120.5 to 119.9 volt is the ripple. The last capacitor Cy, the voltage fluctuation is 2 volts between the peak and the minimum peak. So we are within the margin of IEEE standards of having less than 5% volt ripple factor. And if you look at the steady state condition, all the converters are regulating in the same regulation with very smooth propagations, and reaches the steady state values. And steady state values with the transition from 0 to the maximum value, and they reaches the steady state at the same time. And so this confirms all the capacitors are behaving the unique performances. The classical advantage is here. Look at the gain. So we are trying to figure out this gain from 10% to 30%. So we are going to use only 30% of the input power, only 30% from the PV fuel cell or from any connected renewable energy. We are trying to figure out only 30% to utilize the buses. When 30% is used, we are getting a gain around 22 times. That's a classic. That is a remarkable advantage of using these converters in real-time application. And the most important, once the converter is designed, we have to regulate in real time. Regulation means the loads are not constant. Each load has its own values. For example, I can use 50% of the load. The neighbor can use 100%, and the regulation is different. So this has to be compared. So the loads are not constant. In this case, the power electronics converter has to withstand all these regulation either on the renewable. For example, PV can produce more energy Wind can sometimes produce more energy and has to balance between the fuel cells and batteries. So converter should balance the perturbation from the input side or from the load side and regulate the power for the requirements. So in this case, we try to regulate the load voltage from the maximum value to the minimum value. Say the maximum value is not 400 volt because we have passive effects, EMI, and passive component losses. All the losses goes, we are getting around 395.2 volt. Then we are moving towards 206. So you can see the regulation of the voltage in step by step. And all the cases, the input voltage is kept around 30 volt fixed value. And of course, all the input current are very smoothly regulated, depends on the power of the load requirement. And they are very smooth, they behave uniquely. And the load current requirement is based on the load what we adapted from 395.2 volt to 206. How we done this? By adjusting the device conduction periods. First case, the conduction period of the device is kept 50% and 35%. And last case, we kept 35% each. So we are trying to figure out the converter by regulating, by adjusting these device duty ratio. For example, the experimental results are shown here. We are trying to adjust these device conduction period, and we regulated the converter from a maximum voltage to a minimum voltage, what we fix the margin. And this shows the real-time development. So these are the loads we used and a digital processor to measure all the parameters. And you can see the size of the power electronics converter is very compact. And this is a digital signal processor used to trigger all the MOSFETs or IGBTs in the power electronic circuit. And you can have a complete view on the power electronics converter size is very compact, very small, so that if there is any failure, we can replace the model with a new one because cost effective. Or if a component fails, it can be easily replaced. Of course, again, I show you a result for 250 watts and 350 watts, how the power regulation is going on. So in this case, 30 volt is the input and output is 400 volt. And this is the current on the input side with a very smooth regulation. You can have a look and goes to a maximum current of 4.71 ampere with the average value. And of course, this is the load current for 250 watts. And same applicable for 350 watts, only the change on the load current. The input is kept 30 volt all the cases. And the regulation of the current on the input side is very smooth. This is very important because all the renewables connected, particularly the battery, PV, or fuel cells, this current decides the reliability and durability of the power plants, because this current widely affects the photovoltaic cells or fuel cells, so that the designed units cannot withstand its period of execution. I mean, for example, if it is designed for 20 years, if you have a very hazardous current, or say unacceptable current limits with high ripple factors or huge perturbations, then the lifespan of the renewables can finish within 5 years or 3 years. It's very complex. So we have to be very cautious with the electronics converter to have a very smooth ripple content on the input side as well as on the load side of the power generation. Then we also done simple converters based on SEPIC models. This is a SEPIC converter, is a standard boost converter, buck boost converter, where we try to include 2 inductors and 2 capacitors to balance the power flow. So standard boost converter, but we try to figure out with a new inductor and 1 capacitor. We made it as a new configuration. You can see here. So this is the existing solution of a standard basic boost converter, which is available in the literature. Then we introduce the inductor Ly. You can see here, along with the 2 devices and capacitors is transferred to here. Then we make a new model. So if you look at very closely, the load side is a standard boost converter, and we included additional switched inductor and capacitors. So when the device is closed, the stored instantaneous energy available in L will be delivered to C1. Again, from Ly will be delivered to C2, and summation of these capacitor voltage will be delivered to the load capacitor C3. So we get very high voltage. Once the converter is designed, the most important is the loss analysis. 47% of the loss is provided by the MOSFET, 12% to 13% from the diode. Inductor is around less than greater than 1%, it's around 10%. And for the inductor Ly is only 1%, and for the capacitor is 5%. And between the combination of LZ, C2 and C3 is around 0.4%. So we know what's going to happen in real time with all these last calculations. And important is the efficiency. We are trying to figure out from 60% to 100%. So in 100%, obviously the efficiency is very high, 91.4%. This case, we are not near to say around near to 100. 100 is not possible, at least 99% or 98%, because we use large power components, high rated components, but we are trying to figure out the performance at low voltage, the laboratory scale for various protection, other purposes. That's why the efficiency comes down. Of course, we have passive component losses and switching losses, conduction losses, EMI, etc. So the efficiency comes to 91.4%. Experimental results shown here. Experimental results shown here. The input is around the battery volt of 24 volt. This shows the load current around 0.5 amperes. And these are the currents which is regulated on the input side of the converter, which is very smooth with constant ripple factors. And this is the load voltage, which is 172. So the voltage is boosted from 24 volt to 172 volt, a factor of 6 to 7 times the gain. And these operations are done at continuous conduction mode, which is a linear mode, and all the parameters are considered as a linear parameter. Whereas we are also focused on a non-linear operation for a non-technical, non-background of electronics, that is a discontinuous conduction mode. So in this case, we are trying to increase the power on the load or high frequency to the device, and we observe the characteristics of this behavior of the converter, how it can behave under non-linear operations. Is very important for electric drives because the power electronics converter simultaneously has to charge the battery, drive the motor. During the braking condition, reverse energy from the motor is stored into the capacity as a charging purpose. So these are very important. So for this purpose, we are figuring all the possibilities, even under non-linear condition, which can be verified from the two different levels of the diode voltage, one between 92 volt to 150 volt, which is not happen in linear mode. And of course, the current which is shown for the inductor goes to the P, comes to the zero, which confirms the zero volt switching. I'm sorry, which confirms the DCM, discontinuous conduction mode. And even under the DCM, we are getting around 92 volts from the same battery of 24 volt input. Other applications we have in real time, which is a multi-stage DC-DC converters. If you look at very closely, the input side is a standard inverter, which is connected to multiple stages. So this is available in the market and used in practice. And these stages can be increased to n level, and we can connect to the inverter, and we can able to connect to the grid or to the motor. In the intermediate stage, we can connect the battery and store the energy. Of course, the stored energy can be delivered again back to the motor or the AC grids. So in this case, if you are going to have a zero stage, then it's going to be a standard inverter. If you are going to increase the number of stages until 6, then we require 12 diodes and 12 capacitors. And this is the gain margin we are trying to figure out between 10% to 9% utilization of these devices. Around 90%, we get the maximum value of the gain, obviously. What is the advantage? What are the configuration I discussed today? We never used any magnetic components. There is no transformers or inductors as a resonant circuit between the input power converters and the load side load connected systems. And of course, the current we consider mostly as a continuous current flow from source to the load side. So there is no need of protection for the power supply. Of course, the component used are very low cost for the capacitors and semiconductor devices. So the overall cost of the development of the power converter is very cheaper. And the stages can be increased to very high level because this is a simple combination of capacitors and inductors and diode configurations. And controlling of these power electronics converters are very simple because we can use any standard digital processor because we are not having many devices, complex control, and it's easy to implement in real time. With this presentation, I like to give you some view in real scenario how the power electronics converter play a critical role. So this gives you a clear idea. Power electronics converter play a critical role in real time because we are going to have a DC link. This is a utility grid. From the utility grid, we are going to connect to the AC/DC AC converter. So utility grid is the plugging point, and the converter converts to the DC bus, and the DC voltage available in the DC bus bar. Another side, we have the load application. So for electric vehicle, the motor is a load, which is driven by a motor drive unit, which is an inverter. And you can see the power flow direction. We can have acceleration. Acceleration is from the motor to the motor. Of course, we can reverse the power from the motor to the motor drive, and we can store in the DC bus with the battery storage during the braking on, of course, braking conditions. Another possibilities, we have a DC-DC converters for storing the energy in the batteries or along with the fuel cells for the powertrains. So here we have a bidirectional power flow for charging and discharging from the same DC microgrid point. And here we adapted DC-DC converter for these all power flow directions. And of course, you can have a look on braking. The power from the motor is delivered to the inverter, from the inverter to the DC-DC converter and to the battery. You can see the power flow direction. Of course, during the inversion mode, the energy stored in the battery will be delivered to the DC-DC converter. Of course, here we can have fuel cells and ultra capacitors, and it is delivered to the DC bus bar to the DC-DC converter. From the DC bus bar, we use these motor drives, that is an inverter, to control the motor. So all the operations, how an electric vehicle has been adapted in real time, is shown in a simple way during charging, discharging, power reversal, acceleration, deacceleration parts we have shown here. And many power electronics converters are adapted for these purposes. I can show you some examples. So this is a simple example where in real time we can use a multiple cascading of boost converter. I explained you in the previous stage. Sorry, this is a buck converter on the input side. On the load side, we can couple with a standard boost converter. Then we can power to the load capacitors or batteries to store the energy. Other possibilities, we can use multiple inverters, which is connected on the open winding of the induction motor or permanent motor, where we don't find a star point on one side of the motor. Both sides will have the power supply. So the power supply can be divided into 1/2, and we can enhance the very high power in your drive. The drawback, since all are connected in the same star point, there will be a flow of homopolar components. So the torque is not so good. We'll have multiple frequency and pulsations. And suppose if one side of the power supply breaks or failure, then it's become an open circuit. We need to find a alternative network, how to make a start point on this motor side. Other possibility, we can go for a isolated DC bus. So here I can have a battery, here I can have a fuel cell, or of course we can have a PV panel. So in this case, we can be able to enhance the power of induction motor or a permanent synchronous motor with the open winding configuration. And since these are isolated DC buses, we will not have a problem of homopolar components, which circulates and causes the TDS effects on the torque performances and overheating. Other possibilities I can show you here. We can have hybrid modules like uncontrolled bridge rectifiers, full bridge rectifier, which is connected to a parallel connect boost converter. Then we can able to feed to the load capacitors or ultra capacitors or batteries and fuel cells. So we can enhance the power possibilities. Other possibilities, we can use slow diodes. You can see a configuration where standard invert rectifier, where the top legs are replaced by the diodes and lower devices are controlled. Then we use slow transition diodes to avoid the reverse flow of the current, and we can able to control the power factor here. But the disadvantage, since we are not using a full bridge controlled converter, obviously the voltage delivery will be 1/2. And this is a possibility. Another possibility is we can have a multiple legs extending to 4-leg configuration. 4-leg configuration, we can have 4-leg input side, we can have 4 inductors, and we can able to control the power factor by controlling these devices. Again, the problem here is going to be we are able to provide only reduced voltage factor because these are not controlled devices. And last case is the most prominent solution. Of course, it is available in all electric vehicles. On the input side, we use a high frequency inverter, which converts the DC voltage into an AC format with this is a tank circuit, which transfers the power from the input side of the converter to the load side with a high frequency and a high rate, so that uncontrolled bridge rectifiers are used on the load side. And by using a large size capacitor, we can filter out all the ripple content, and we can able to store the energy in the battery, or we can use fuel cell, etc., for parallel operation of the converters in EV. About I go to next topic, because we have seen many configurations. In many configurations, we use the buck converters, buck boost converters, and interleaved boost converters. And of course, we can use 0-volt switch full bridge capacitor based output filter converters. What are the advantages and disadvantages? If you look at the first case, is going to be step up, step down. Second case, we can have step up and step down. Third case, we can able to control the input power factor, of course, in the fourth case. And the fifth case, we use always a high frequency inverter on the input side to convert high frequency voltages either from the AC or DC. In all these cases, the application is focused on sending the power to the battery in the first one. Second case is used for regeneration. Last 3 cases are used for charging of the batteries. What are the key features? In buck converter, we can go for continuous, of course, non discontinuous mode. I can say linear and non-linear mode for simple understanding. And second case, buck boost converter, we can go for 4-quadrant operation. We can go for motoring, braking, regeneration, etc. And the third case is important because EMI is very less, so we need a small input filter to compensate EMI. And fourth case, we doesn't want a rectifier on the input side. The last case, we have to adapt 0-volt switching so that the power transfer from the input side to the load side will be very high. Then the most important technology is on wireless power transformation, because wireless power transformation plays a critical role along with the electronics converters. The source size is a grid, or it can be a AC power generation, which is connected to a rectifier, which is based on a MOSFET or IGBT. The DC power generated, the high frequency, will be delivered to a contactless transformer with a ratio EM, so that we can able to deliver the high frequency signals from the primary winding to the secondary winding, or technically we say transmitter to the receiver. It's nothing but the coils, high frequency coils. Then the load side, it is connected with the uncontrolled bridge rectifier, and we can have a HP batteries for storing the energy. And this is a prominent solution for wireless power charging between electric vehicle and the power grids. But this is a classical model. The recent technologies, of course, in China, they adapted along with the model called OLPT, which is a resonant inductive power transformer. The tracks, they have the inductance coil, high frequency coil will be laid on the tracks where the car is going to be traveled, and they are connected to a 3-phase AC or DC inputs on the track sides. On the vehicle, we'll have this setup. So on the vehicle, we'll have another pickup impedance, which is an high frequency coil. And from the pickup coil, we transfer the power to an controlled bridge rectifier. Then we use switch mode power converter, and we can use for a battery for the storage, or of course we can use for powertrain. So this is the recent technologies which is available in electric vehicle. You can see all the cases we need DC-DC converters and power electronics components to control the power flow from the transmitter to the receiver. I mean the two coils. About the technologies, I can give you a quick outline. We can have inductive powerless charging stations. We can go for a capacitive powerless charging stations. The limitation is going to be between 6.6 kilowatt to 50 kilowatt, and doesn't going to create any pollution to the environment. Pollution plus free technologies these are. And here in this case is primary and secondary coil or C. That's most complex one. And of course, there is a losses in the system because of the coil. We can have ED current losses, EMI effects. These are going to be a non-linear behavior with a flux distribution. About CPVT, we can have multiple applications. We can use capacitor for this purpose, but the cost is going to be very high because of the capacitor size, and we need to galvanize the isolation part. That is also an expensive applications. And in this case, we have again a two coil, which two coil are done with the transformers, and they are going to work as a transmitter and receiver. And about the cost, other parts, the power application is going to be cheaper, and this is not preferred for high voltage application. And of course, it's this is a model which suffers with electronic component design, and much not preferred this model. Other possibilities, we have a permanent magnet coupling power transfer model. Permanent magnet coupling transfer model, we are going to use the permanent magnets motors, and because of that, we can able to get a very high controlled flux distribution in the air gap between the powers, I mean from the stator to the rotor. And the most important here is going to be 150 millimeters should be the distance between the transmitter and receiver. And this model, we don't want to have any noise, vibrations, and that is an additional advantage. Of course, the lifetime is very important associated with all the mechanical components. That is very good. And about the rotor side, since it is a permanent magnet, we will not have much effects of rotor harmonics or losses on the rotor side, I mean the transmitter between the receiver sides. And another possibility, we can go for inductive power transfer. In case of inductive transfer, the most important is the 40 centimeters, the distance between the transmitter coil and the receiver coil. In this case, the efficiency is very maximum, and challenges lies with impedance matching, magnetic coupling, and current variations. And these can be done by coupling multiple resonant converters. This is multi stages of coupling of parallel operation of resonant converters. We can able to enhance the power. Advantage includes you can go for any range of power supplies, power requirements, and EMI is much less, and it can be operated for high frequency. You can go for megahertz operations, but the efficiency is also very good. Another possibility, we can go for online power transfer technologies. In this case, online power technologies are likely a choice, but it depends on the road condition. So it depends on the condition of the roads, and of course we can use low resonant components here, low power resonant components for utilizing for high power applications. And we can use primary winding as based on the road tracks, and secondary winding on the car, so that efficiently we can keep 30 to 40 centimeters of the distance as like the previous version. And implementing this technology mainly depends on the cost factor, very expensive to go for this technology. And this technology we can go for very high voltage, which includes three-phase systems, AC power supplies. And another possibility, we can go for RAPT, which is a resonant antenna power transfer systems. In this case, two antennas are required, and the two antennas should be very tedious to design. That is a task to have an identical frequency. They should have an identical frequency between the transmitter and the receivers, and the distance we can go up to 10 meters. That is the classical advantage. And the frequency we can go up to any megahertz for a wider range, high power applications. But again, the complexity is in designing such two antennas. I mean, the two coils of having 10 meter in distance and frequency matching. That's the big challenges. And these are the impacts of electric vehicles. The impact on electric vehicles, we have different impacts. We can have an impact on the grid, we can have an impact on the environment, we can have an impact on the economy. So in economy point of view, we can have a low operating cost. We don't have going to have a very expenses on the operating cost. And the benefit is we can be able to have a vehicle to grid or grid to vehicle applications, and we can be able to control the power from the vehicle to the grid. So as an entrepreneur, we can be able to supply power also to the government, of course from the home. That technology is in the near future. What is the impact of the environment? We are not going to emit any hazardous gases. So greenhouse effect is compensated by a factor what is required, 70% by 2030. And about the grid, we have a positive impact because we can able to have a smart grid systems, and we can able to have a V2G and G2V control, and we can able to integrate different renewable energy with the grid. What is the impact? Since we are going to integrate multiple renewable energy and communication between vehicle to grid, grid to vehicle, we will have instability problems, voltage instabilities. During the peak, demand may increases because multiple renewables cannot give you the sufficient enough power. For example, wind and PV, we have variations. A lot of harmonics can be generated from the power electronics converter, so we need to compensate all with the filters or PWM techniques. Then we may have swell and sag with the voltage fluctuation because of the integration of different renewable energies. Of course, we can have a lot of power losses, and of course we can able to overload our transformers. So these are going to be the challenges for the future impact of the power electronics converters. And this gives you how the impact can be controlled. We have power generation units, and this is the energy market, which is going to be a bidirectional between the power generation and the consumer sides. And we can create a VPP control unit. From the VPP control unit, we can able to control the EV fleets and the distribution organization and transmission system organization. So here the dotted lines shows you the control of communication between the flow of whatever we need the communication, and the dark line shows you the power flow, how we can control the power between the requirements. So power generation to the consumer. So from power generation to the consumer is given to the transmission system, distribution system, and the consumer. Standard model of the grid. But intermediate, we are going to create a energy market which includes EV. So energy market to analyze the balance between the power generation and the consumer needs, and VPP control monitor all these parameters from the consumer end, of course from the power generation, and able to control the energy market requirement, which fluctuation we are going to control with respect to the renewable or with the communication between V2G or G2V. And we have a EV fleet for the charging station, which can be connected between the distribution system, of course VPP control units. This gives you a clear idea how we can have a standard smart solution for EV power generation along with the grid. And with this, I can give you the overall scenario of EV in the world. Presently, EV is dominated by the Chinese companies in 2016 by BYD, which produces PHEV, So plug-in electric vehicles play a critical role in real market in 2016. And in 2016, again, the top seller were Tesla. They used fuel cell based electric vehicles. So fuel cell along with the battery is their model. They are very prominent. And with about Tesla models, we have our Renault also in the market. They use battery electric vehicles. They sold around 21,338 units in 2016, and Nissan around 18,000 units. Mitsubishi also uses PHEV, plug-in electric vehicles. They sold out around 21,333 models in 2016. And Volkswagen from Germany, they used both PV battery-based electric vehicle and plug-in electric vehicle. They sell out around 13,300. So you can have a look how the market has been dominated by these companies in 2016. So Tesla plays a critical role. And this shows you a clear idea what are the markets which is available for electric vehicles. BEV market in 2016 are dominated by these companies, out of which Tesla plays a critical role with a battery electric vehicle. And about a plug-in electric vehicle in 2016, the Europe, how the market looks between various companies from Mitsubishi, Volkswagen, and Mercedes, Volvo, and others. So you can have see a look. The most of the things which is other major, I said in the beginning, Chinese always occupies the major role. And what are the trends in the future? For sure, the trends and the future of the electric vehicles along with the power electronics converter, we need to have a smart VPP system. So we need to include smart metering systems in our sustainable EV electric technologies to be integrated with the renewable energy systems, which includes PV, battery, and fuel cells. And of course, the electric vehicles are to be designed based on fuel cells in combination with electric vehicle for a good solution. In this case, we can have a high power density and non-toxic materials when we are moving to a complete electric vehicle. Of course, we need to reduce the cost and the weight. In this case, battery can be a good option. Lithium technology is going to be the potential market in the future. And as I said, the future is focused always on V2G, better charging technologies. We need the technologies. Then we need a better batteries to do these technologies. And powerless transmission is going to be the future for the electric vehicles, of course, for the overhead power supplies. In conclusion, I can give you that I have presented many power electronics converter from our own investigation. Of course, from overall scenario, how it can adapt the benefits for the sustainable growth of the environment. Fuel cell going to be a critical play. Fuel cell along with a battery can be a solution for the future. In this case, lithium battery is going to be the challenging future because presently it is very expensive, and we can't use lead acid batteries because we have to say goodbye to them of their poor reliability and charging condition of unable to control the state of the charge. Therefore, in future, we can also look for other possibilities away from lithium battery. One possibility, we can go for metal air batteries technologies. Then we can also look about how to use lithium sulfur batteries. And now we can use zinc battery technologies to increase the potentiality. Of course, we have a choice of a competitor, is ultra capacitor, which can be able to store very high power density when comparison to all battery versions as a parallel operation. Then, of course, these power electronics converters creates a lot of limitations to the grid, and we need to control all these voltage profiles with compensating the sag and swell. Of course, we have to control all these perturbations with proper smart controlling systems between vehicle to grid and grid to vehicle. And of course, we need to compensate the harmonics which is generated with the power electronics converter to have a smart system. So still, there are a lot of rooms left in the developments of EV with the renewable energy integration to the grid to have a smart microgrid systems. Thank you one and all for your attention. If you have any question, I'm happy to respond.
So very good presentation we have received from Professor Sanjeev. And if anybody want to ask any question, they can write the question in the chat itself. We have new message. Professor Bhupen says, thank you, sir. It is a good presentation.
Thank you. Dhanyawad.
And if anybody want any queries, any lectures, they can raise their hands. And then I can open their mic. to speak you. So I think there is no query. Everybody is satisfied.
Okay. If you have any question, please email to me so that I can, you can email to Dr. Bharadwaj and he can ask me so that I can happy to respond to you. Thank you for providing this opportunity, because with the short schedule, I can't present more details because it's a very scheduled time. So in another occasion, I will present you more reviews on electric vehicles. We have many technologies and battery technologies are going on. I given you only an outline. I will give you next presentation or next occasion to meet you all. I can provide you more solutions, which is
Okay,
available
thank
in
you very
real
much.
time.
Now I request Madam Shukla to close the session. Madam
Okay, sir.
Shukla, please.
Sir, thank you very much for this such a wonderful and informative session. And I am definitely sure that our participants must have got benefited with this. So, sir, we are definitely looking forward for much more sessions from you. So in future, we will definitely would like to go for that. Thank you very much, sir, for being
Thank
here
you.
with us.
Okay. Thank you. Bye. See you all.
Thank you, sir.
Dhanyavad. Thank you.
So the next session will start at 1:45 in PLC or Drive Lab. Everybody is requested to be there at that time. Okay, thank you very much.